Okay, so let's have a look at some more applications. We actually have been touching them throughout the exercises, but we'll look at some specific ones today. Now, relevant at the moment, let's say the coronavirus has been doubling at a rate of approximately every 4 days, so it takes 4 days to double. I'll start by modelling with a 2 to the power of, because 2 means it's doubling. I'll get the number of days. That means it's doubling every day. So if I divide it by 4, that means that it's doubling after 4 days. I'll have 2 to the 4 on 4. It's doubled. After 8 days, I'll have 2 to the 8 on 4, 2 squared, which is 4. So now it's doubled twice, etc. So we can actually use that, and you could play around with some modelling software to see how that's working. Okay, so first of all, let's have a look at a simple example here, just involving population growth. So if we read the question, the rabbit population is increasing by 25% every year. So what it means, it's growing by 25%. So it's 125% of its original amount each time, or 1.25. And this is what we call the growth factor. It's growing by the whole amount plus an extra 0.25, hence the 1.25. We're going to estimate there are currently 500 rabbits on the island. So when t is 0, we're expecting the rabbit population to be 500. So now expression for the population, we'll call it P, will just be 500 times the growth factor to the power of t. So after 1 year, we'll be timesing it by 1.25. After 2 years, we'll be timesing it by 1.25 squared. And this is our general setup. So this is always the initial value. We'll call it IV. And this is the growth rate. We'll call it 1 plus R if it's growing, 1 minus R if it's decaying, and then the power of t if it's growing every year. How many years will it take the rabbit population to be 10,000 rabbits? So we're going to change population to 10,000, and we'll need to solve to find t. Now, if it's a multiple choice, you could just do trial and error and get the right answer. But we know our logs, so we're going to use them. So step 1, we're always going to divide by that initial value first. So I'm going to divide both sides by 500. Cancel them off, and so that will be 20. And again, we could keep doing trial and error till we get a number bigger than 20 or around 20. But what we're going to do is we're going to take the log of both sides. We're going to bring down the t in one step, and to get t, we're going to go log 20 divided by log 1.25, and we're going to do that to the nearest tenth of the year, which will mean 1 decimal place. So grab your calculator and we'll check this together. And I got 13.4 years. One way to check that is we could put it back in this equation here, and we should get an answer about 10,000. Let's have a look at this second example now. This time we're going to look at exponential decay. So have a moment, pause the video and read the question. What we'll notice in this question is decaying such that each month there is 1/5 as much of the previous isotope left. So basically it's decreasing by 4/5, and R, our rate of decay, will be 0.2. There'll be 1/5 or 20% left each time. So it's really important that we always work out what's remaining, not what's disappeared. And this question's a nice one. It doesn't try to trick you. A lot of others will. So in part A, we just have to fill in the table to show how much is left. So basically, we're just going to times it by 0.2 each time. And usually we go to fractions, but I think with this one, I'm going to go to decimals. It's going to get a bit messy, but I'm okay with it this time. If we've got really messy, really horrible long decimals, I would be going to my fraction. So now we're going to find a formula for the amount remaining after t months. So we know that originally, so we'll call it A for amount. Originally we started with 1 kilo, and I'll write 1 here, which seems a bit silly, but it mightn't always be 1 kilo. We start by writing what we have. Then we times it by, in this case, the decay rate to the power of time. And I'm guessing we'll go T for months. You can then drop the 1 if you like. I'll just leave it there. It doesn't really matter. Now we're going to graph the curve. So the first thing up the side is I'm going to write the amount or the mass, whatever you want to call it. And I need to go up to kilos, so I went up by 0.2 this time. So when T is 0, so this axis will be T. When T is 0, the mass will be 1. When T is 1, I need to drop straight down to 0.2. When T is 2, it's going to be so small, you can see I'm hardly going to be able to graph this one. It's not the best scale. But now we're going to try and make an exponential decay curve. And never touch the axis, but get very close. So how do I work out how much is remaining after 7 months? Well, there's no way I could estimate it for my graph, and I shouldn't use my graph unless it says to use your graph. We should always go back to the formula. So all I'm going to have to do is go 1 times 0.2 to the power of 7, and this is going to be absolutely gross. Grab your calculator, you'll see. Really small number in kilograms. We'll write it 4 zeros. And that's fine to leave it like that. If I times it by 1,000, I could put it in grams. Maybe that makes a little bit more sense. Grams. Or I could times it by 1,000 and put it in milligrams if I like. So hardly anything left after 7 months. It's decaying very quickly. Okay, let's have a look at a few harder examples now, a little bit more of an extension. First, the Richter scale. So that measures the magnitude of an earthquake, and it measured in logs to the base 10. So if your earthquake goes up by 1 on the Richter scale, it's actually going up by a factor of 10. If it goes up by 2, it's going up by a factor of 10 squared, so it's 100 times stronger. Okay, if it goes up by 3, it's going up by 10 cubed, 1,000 times stronger. Okay, so it's a really good measure of things that have a great amount of variation in their intensity. So first of all, I want to use the find R, which is the magnitude of the earthquake. That is 4.3 million times more intense than its reference intensity. Okay, so basically I've got one earthquake and another one that's 4.3 million times more intense. How does that compare on the Richter scale? So first, let's write the formula. So all I'm going to put in here is my intensity is 4.3 million to 1. That's as a ratio. And let's see what that is on the Richter scale. We get 6.6. Okay. So you can see 6.6 on the Richter scale. When you compare it to an earthquake of magnitude a lot smaller, it's a lot more intense. It's 4.3 million times more intense, whereas 6.6 doesn't seem like such a big number. Okay, so an earthquake measures 8.5 on the Richter scale. How many times more intense is this than the reference? So basically we have our formula. And we're trying to work out what this is, how this one compares to that. And as a ratio, I just like to think of it as to 1. So we're going to put 8.5 in here. It's a 10. So the ratio of I to I naught will be 10 to the power of 8.5, which should be a fairly large number. Okay, and yes, it is 3, 3, 3, very big. Okay, the next example we use are decibels. And again, you're not expected to remember all of these formulas. You'll be given the formulas, the explanation of what they are, and then you'll be expected to use them. So here we have a formula that measures the loudness of sound, again compared to a reference level. A sound that causes pain in humans is about 10 to the 14 times more intense than S0. So it's saying this here, inside this bracket, is 10 to the 14, because S to 0 is 10 to the 14. Find the L for a sound, L, the loudness of this. So easy, I'm just going to put that in, 10 to the 14. Maybe I'll do it without a calculator just for fun. So I'll bring that power down. Log 10 of 10, gone, 140. But we could check by putting it into the calculator. Always go back and check if there's any units in our questions, but we're good here. How many times more intense is the sound of a heated argument, about 67 decibels, than a sound of a quiet room, about 31 decibels? So basically we've got our argument. And this is about 67 decibels. We have our quiet room, which is at 31 decibels. Okay, so after we've done that, let's see what the difference between these two is. So I'm going to minus those two equations. On the left-hand side, I'll get 36, and I'll have this log minus this log. Notice I've put in here a little a, that's sound for the argument, and this one here is the sound for the room. Okay, so now let's combine our logs. So first I've divided everything by 10, and now I'll combine my log. So 3.6 equals log SA S0 over SR to S0. Let's cancel those reference levels. Okay, now let's rearrange that. So this is a 10 to the power of 3.6 is the ratio to the sound of the argument to sound of the room. And 10 to the 3.6 are reasonably big. So we'll go 3981, sound of the argument to the sound of the quiet room. So we can say the sound of the argument is 3,981 times more intense than the sound of a quiet room. And you should write a nice little sentence there explaining that.